Testing strategies to select for a specific analyte. Measuring an analyte when it's present in a complex mixture of biological molecules. Explain how to measure an enzyme analyte or an analyte that is substrate for an enzyme. This is our aim. Measurement of one substance which is part of complex mixture of substances provides special challenges. A measurement method that works well for determining the amount of analytes in relatively pure form may be completely unsatisfactory when the analyte is in a mixture of salts, proteins, lipids, carbohydrates, trace minerals. Method for analysis of analyte in complex biological mixture requires special approaches to minimize or eliminate interference from other substances. Some of the approaches frequently used in clinical chemistry, such as blanking, rate methods, pre-treatment, reagent specificity, and ion-selective electrodes. Blanking for endpoint reaction. Blanking is a term that describes a correction for background constituents that contribute directly to the signal being measured. In the case of calorimetric reaction, blanking measures the innate background color in the sample. Subtraction of background absorbance from the final absorbance ensure that the background color is not inappropriately attributed to the analyte. For example, in the measurement of albumin using bromocresol grain, the amount of albumin is calculated from the absorbance of light at wavelength 628 nanometer. The light absorbed by the green-colored albumin dye complex. The absorbance is used to compute the amount of albumin present based on calibration curve. However, if other substances in the blood sample also absorb light at 600, if other substances in the blood sample also absorb light at 628 nanometer, their absorbance reading could be incorrectly attributed to albumin, and the resultant albumin concentration will appear to be higher than it actually is. To correct for these other substances, the absorbance of the solution may be measured prior to the addition of the dye, and only the change in absorbance above the initial value is used to compute the albumin concentration. Alternatively, the sample may be diluted with non-reactive solutions such as saline in a second cuvette, and the absorbance of the diluted sample can be used to correct the result. Blanking correction. Blanking correction for the contribution of interfering substance by subtracting the signal period to addition of reactive reagent from the endpoint signal. Absorption A due to analyte equal to A at TF minus A at TV. This is the sample added, the blanking zone, the final absorbance. Here A due to analyte TB time, the time of the initial reading, TF time of the final reading. Here reactive reagent added, three common interfering substances that are found in plasma and serum are hemoglobin, lipids, hemoglobin from the red blood cells, lipids such as triglycerides that in high concentration result in a turbid cloudy solution, bilirubin, a yellow-orange colored product formed from the breakdown of the hemoglobin. These three substances are so commonly found in samples that a special approach is used to assess their presence and correct for their interference in optical analysis. Use of selected time windows for rate reaction. Sometimes several substances present in the sample react with the reagent to produce product that absorb light at the same wavelength as the product from the analytes. In such a case, blanking for addition of the reactive reagent will not correct for the interfering substance, since the color does not form until the reagent is added. However, in many cases, reaction conditions such as pH of the solution or concentration of reagent can be chosen so that the interfering substance reacts at a different time than the target analyte. The interfering substance may react faster and be consumed before the target analyte, or may react more slowly and contribute little or no signal in the early time frame of the reaction. If the interferent reactant more rapidly, measurement is taken at time point late in the reaction course, when the rate of color change reflects only the target analyte. If the interferent reacts more slowly, measurement is taken at time point early in the reaction, when the color change is primarily due to the target analyte. An example of the value of using timed window in a rate reaction is seen with the GIF method for creatinine. In the GIF reaction, creatinine reacts with a solution of alkaline bicarate to form a red-orange product. Unfortunately, many other substances found in the biological samples also react with alkaline bicarate to form red-orange products. Some of these include acetone, acetate, and protein. It was found that acetoacetate reacts completely within the first 20 seconds, and protein demonstrates a lag time, reacting only after 1 or 2 minutes. So a time window that begins sometimes after 20 seconds and ends within the first minute will reflect product formed from the creatinine with little interference from either acetone or protein. The rate reaction with measured time chosen to reflect target analyte. Here the sample added active reagent, reacting of interfering substance, reaction of target analytes. The absorption A due to analyte A at time 2 minus A at time 1. Pre-treatment. Sometimes it's possible to treat the sample prior to analysis to physically or chemically remove potential interfering substances. Pre-treatment be done offline or online. Pre-treatment performed offline means that the treatment is done in a manual step before the sample is loaded on the automated analyzer or placed in reaction cuvette for analysis. Pre-treatment performed online means that the treatment is automated on analyzer and is carried out as part of the total analytic process, usually in the same reaction cuvette that is used for measurement step. Measurement of high density lipoprotein sample cholesterol, typically about 25% of the total cholesterol in serum, require remove of all non-high DL, HDL cholesterol, such as low density lipoprotein LDL and very low density lipoprotein VLDL cholesterol. Prior to measurement steps, the pre-treatment can be done offline or online. Offline pre-treatment involves mixing the serum with an agent such as polyethylene glycol that react with non-HDL cholesterol particles. This step is offline pre-treatment because it's carried out manually and not automatically on an analyzer. A sample of serum is mixed with EEG and precipitate containing the LDL and VLDL particle in form. The precipitate can be forced to bottom of the tube by centrifugation leaving a clear solution that contains the HDL. The clear solution is used as a sample for HDL cholesterol. The test involves treatment with reagents specific for cholesterol, such as cholesterol esterase, that produces a product that can be measured photometrically. Online retreatment. An online approach involves a two-step reagent treatment of the sample in the reaction curve rate. The first step, produce a reagent, cholesterol oxidase, that selectively destroy the non-VHL, HDL cholesterol that is not bound to lipoprotein, leaving only HDL cholesterol in solution. Second step, detect the remaining HDL cholesterol by its reaction with reagents specific for cholesterol, such as cholesterol esterase, to produce product that can be measured photometrically. Exhibition syndrome, BAG, centrifuge, offline treatment, and this is online treatment. The transfer solution to test for the HDL. Here the HDL, here the low density lipoprotein, very low density lipoprotein, the green one. Cholesterol oxidase, patient sample, cholesterol oxidase directly for HDL. Choosing methods that are highly selective. Enzymes are biochemically catalyst substances that increase the rate of biochemical reaction without being consumed in the reaction. They are often exquisitely selective for one or only one chemical substance. There are often exquisitely selective for one or only one chemical structure. A chemical structure that is specifically acted on by the enzyme is called substrate. Enzymatic reaction can be used for determination of either a substrate concentration or an enzyme activity. An enzyme is a biochemical catalyst, a substance that increases the rate of the reaction without being consumed in the reaction. Each enzyme catalyzes conversion of specific molecule referred to as a substrate. Here the substrate, enzyme substrate complex, the product. Enzyme cleavage substrate to produce photometrically measurable product. Detection of the substrate for many analytes in biological fluids such as glucose, cholesterol, bilirubin, creatinine. Nature has provided enzymes that selectively react with these important molecules. Such as enzyme can be used to catalyze the conversion of the molecule substrate in reactions that generate products that can be observed photometrically. For example, glucose can be converted by enzyme hexokinase to glucose 6-phosphate, which in turn can be used to produce a molecule of nicotine adenine dinucleotide, nicotine amide dinucleotide, NADPH. For each molecule of glucose, one molecule of NADPH is produced. NADPH can be measured in the ultraviolet region at 340 nanometer. Detection of biological substrate like glucose can be carried out as an independent reaction by measuring the maximum amount of NADPH formed, or as a rate reaction by measuring the rate at which NADPH is formed. Glucose plus NADP taught glucose 1,5 lactone plus NADPH.